as of right now, I'm recording. Okay. Questions 1 through 3, I think Jessica said. So this number 1, interactions of the following 2 atomic p orbitals would result in what kind of orbital and in the orientation shown. So can you see my pointer, Jessica? Okay, good. So because these 2 are coming at each other in this way, so can everybody see me too? Right, so because those orbitals are coming this way, it's going to be front overlap. And because they're constructive, so that both of these 2, the black and the black, are facing in, so they're constructive, they're not destructive, so it's going to be a bonding orbital, and it's going to be a sigma bond. So I'm recording again. So question number 12 on 3B. So here's 12 on 3B. So if I were going to draw the all of the resonance structures for this hybrid, so I'm going to share my screen real quick here. And I don't know how to draw on Word documents like Cambry can, so I will now share my, did everybody see that? I will now share my iPad. So the question was, we have benzene ring here, the double bond here and a double bond here, and a negative charge here. So I go ahead and draw the electrons in there. So it wants to know all of the resonance structures possible for this species. I take a look at these 2 electrons, and that's where I'm going to start my electron movement. And so these 2 electrons, I'm going to kick them into a bond right here. And then the pi bond on this carbon hops up onto that carbon. So my first resonance structure here is going to be this. So the new double bond is there, the negative charge is there, and the double bond stays there. And so that's my second structure. And then if I keep going, I'm going to change colors so you can see what I'm doing. So if I keep going, this lone pair can move here. And then this double bond breaks and moves up here. And so my next structure looks like this. With the double bond here and here, and the negative charge here. So I originally, when I look at the first molecule, I say, where's my negativity, where's my charge, whatever. So the way that I look at this is I start with that first one, I say, where's my negative charge, right? And so, if we look at those patterns, right? So this is a lone pair right next to a pi bond. So allylic lone pair is definitely going to be one that is a pattern that we recognize that can have resonance. So let me answer the question now. So if we take into account that we have 3 resonance structures and we've got to pull them all together, the way I would draw my resonance hybrid would look like this, where I have partial double bond here, partial double bond here, partial double, my finger's not drawing very well. Partial double bond here and a partial double bond here. So that's like right in here is where I have the negative charge moving. And then you can just draw a negative sign there. Or you can draw the benzene ring and you can say that there's a partial negative here, a partial negative here, and a partial negative here. I would draw the dotted line here too.
One question I had was with like specific to resonance structures, how do you determine the major and minor contributors in them?
Stability of contributors. So rule 1, the first rule, and you got to do these in order for sure. So the first rule is that we got to have octets. So the most stable one is going to have everything with octets. And so when you have a carbocation, that throws that out the window. So if you have a carbocation in one structure and the other structure has all filled octets, the other structure is more stable. The second rule is that we want the one with fewer formal charges. So if you have one structure where we have 3 formal charges and another structure where we just have one with 3 is definitely less stable. And the third rule is that we want the negative charge on the atom that's the most electronegative. And so you have to do it in that order. So even if both rule 2 and 3 are followed, but you don't have an octet, that one wins. Eva, did you have any specifics that you wanted to talk about?
So I have the answer for week 3B, question 13. It asks about significant resonance structures. How do
Okay.
you know like which ones are significant versus like an insignificant one?
And I talked about this a little bit in my video. Did you get a chance to watch the resonance video yet? Like any alkene like that, let's say it's in this molecule right here. Technically, you can move the electrons this way where you just kick these up. And so your resonance structure looks like this, where you have a positive charge here and a negative charge here, right? You can do that, but that's not going to be a major contributor. The major contributors are going to be the patterns that we talked about. It's these right here: allylic lone pair, allylic carbocation, lone pair adjacent to a carbocation, pi bond with two atoms of different electronegativities, and conjugated pi bonds. You know, these are the things that are going to happen, and these are the things that are going to contribute to our most stable resonance structures. So we have an allylic lone pair where the lone pair kicks down and then that double bond pi electrons hop up onto the carbon. And if you watch my video, I go through and I draw what those resonance structures each look like. So these patterns are the primary things we're going to recognize. If we start taking like that double bond and just kicking it up and making a positive and a negative right next to each other, we can do that, but these patterns are the ones that are going to give us resonance structures that are really contributors, major contributors. And again, the video is pretty long, but I really spend a lot of time showing you how I think about solving resonance structure problems. So take time to fit that into your schedule because I think it'll be helpful. Did anyone on the Zoom meeting right now watch it already? So Madeline, can you reiterate that it's worthwhile to watch, or did you find it confusing, or what do you think?
It was definitely worthwhile to watch, and then going and doing like some of the testing, whatever's on Sapling was extremely helpful too.
Okay, perfect. What did you log on thinking that you needed to accomplish?
Number 5 on the week 3B SI sheet.
Okay, number 5. Okay, so what patterns do we recognize here? So we have the lone pair here on the oxygen, right?
Yeah.
Next to the double bond. So that's one pattern that we know about. And then we also have a carbocation that's allylic to the double bond here and allylic to the double bond here. So there's 3 different things we can do here. We can kick this double bond over here to fill that p orbital so that we have a positive charge at the end and a double bond here, and then leave the rest of the molecule the same. Answer number 3. So do you see how we move this pi bond 2 electrons in to fill that empty p orbital, and then the positive charge ends up over here. So we end up with number 3. So number 3 is an answer.
I see that, yeah.
You see that? Okay. So that's 1. Now I go back. You can keep going with that one, which it's hard because the positive charge is way at the end of the molecule. So you can either keep going with that one and try to move things, or you can go back to the starting one and move that. So I'm also thinking that this pi bond can move over here. And so we have a double bond here, and then the positive charge would move here. So that's answer 1. Do you see that?
Yes.
Okay. And now the last one I see, I think it might be easiest if we continue from that. So I guess we can go from this structure right here. We can then take the lone pair and kick them down. So then we end up with that p orbital's filled, and then the oxygen has a positive charge. So this one right here. So the answer is 1, 2, and 3. The way that we can very easily throw number 4 away is that in our starting molecule, that carbon right there is sp3 hybridized and we can't touch it. And so in answer number 4, that positive charge is on the one that was sp3. So there's no way that we can do that. In order to have a positive charge, it has to have been sp2 hybridized from the beginning, or be an oxygen. In your video about the exam, you said one of the topics is hybridization and bond angles. Do we need to know the exact numbers of bond angles? You mean like Vesper theory, like the 104 and the 107 and the 109?
Yeah.
I think I didn't do that. So it's either 109, 120, or 180.
Okay.
So you can say approximately 109, approximately 120, approximately 180.
Okay. Thank you.
Yeah, I don't think I got that specific. But I hate teachers that are just like, no, that's not on the test. You don't have to know it. So I'll just tell you what it is anyway, right? If you have lone pairs, then that pushes them. So a nitrogen with 3 hydrogens, those are going to be 107 instead of 109 because the one lone pair pushes down. 2 lone pairs on oxygen with water, it's 105 because it pushes them even more. So Vesper theory, electron repulsion, those bond angles are going to shrink because the lone pairs take up a little more space than a bond. In the video for the exam, you mentioned doing curved arrows to represent a chemical reaction. Can you do a practice problem on that?
I think it might be like number 20 in chapter 3, but I'm not sure.
So this is an example using acids and bases where we have a chemical reaction happen and they want us to draw arrows. I look at this problem right here and I see that we have a base right here because it's negatively charged. And then I recognize this very quickly as a carboxylic acid. And so then I think that is my proton donor, right? So OH minus we recognize as a base and carboxylic acid we recognize as an acid. So this is going to be donating the proton and this is going to be accepting the proton. So we want the double-headed arrow and we're going to grab this lone pair and that lone pair is going to form a new sigma bond to that hydrogen. So that lone pair makes a new sigma bond with that hydrogen. And then these electrons in this bond hop onto the oxygen. So when you do resonance structures, you can only touch pi bonds and lone pair electrons. But when you have reactions happening, you can actually break sigma bonds. So these 2 electrons are going to hop onto that oxygen to give you the product over here, which is water and then this conjugate base. So the conjugate acid and the conjugate base. Okay, so when I think about chemical reactions, drawing the arrows, the first thing that you should do, which I didn't tell you, is to look at the products. Like I recognize this as an acid-base question, so I knew what was going to happen. But if you look at a problem and you're like, what is even going on? And it's maybe a reaction you've never seen before, look at the products. So from the starting materials to the products, let me go back. Does it still have my answers in there? No. Okay. So if I just look at this problem again, if I look at the products, I know, look, I have OH that turns into H2O. So I know that this oxygen has to make a new bond with a hydrogen. And then I look at this species and I'm like, oh, okay, this one lost it. So even if it's not a simple acid-base reaction that we know and we recognize, it could be something crazy that we've never seen before. Just look at the products, because I won't ask you to draw the arrows if I haven't given you the products, right? Or I could ask you, here's the arrows, draw the product now. So then you'll have to follow the arrows and move those bonds and draw the product. Or I could say, here's the starting materials, here's the product, draw the arrows that would make that happen. So I can ask it either way. Does anybody have any thoughts or questions? Or usually people are a little more frantic. Is it just because the test isn't until Tuesday, or is it that you feel comfortable? Like usually I don't have enough time. In an hour review session, I don't have enough time to answer all your questions. Maybe as the material gets harder throughout the semester, that's what happens. But it is kind of a nice little chunk of solid, pretty straightforward material. I think the hardest parts are the resonance structures, and then this whole acid and base thing with trying to figure out which one's the strongest acid, which one's the strongest conjugate base, or whatever, however I ask it. I think those are the 2 pretty challenging pieces. And then the Lewis dot structures and the formal charges, I think those are pretty straightforward, but if that's new to you too, then that might be something else to focus on. Certainly I have office hours tomorrow, which are actually pretty booked with the people that haven't met me yet before the first test. But if you guys have questions for me, absolutely don't hesitate to send me an email. if you do a screenshot of the question you have, it's easier than trying to explain it. So picture's worth 1,000 words. So if you do a screenshot, send it to me and yeah, I think we should be good. Did you guys get the sapling done that's due tonight? Good. All right. Cool. Have a good day. We'll see you Tuesday
you.
morning,
Thank
bright
you.
and early.
Thank
You're
you.
welcome. Bye-bye.